Hi, let's look at HCl addition to the pi bonds, the alkenes. H is an electrophile and X is a nucleophile in this case. And also the pi bond, the electrons are nucleophilic, attacks on the H, the electrophile, and rupture the bond between H and Cl. So this can take two ways. That's actually primary carbocation and tertiary carbocation creation. And in order to make the primary carbocation, so you need to have a positive between the first on the first carbon, and tertiary carbocation where you have three R groups attached to the carbon plus. Right now the H location is different. See, if the H goes to the right of the double bond, it makes the primary, and if it goes to the left of the double bond, it makes the tertiary carbocation. So let's mark the primary carbocation here because it has only one carbon extending further, and here this carbocation is attached to three R groups. It's called the tertiary carbocation intermediate. So every carbocation is an intermediate. Now, so we can also look at this one. So more chances of getting to the tertiary carbocation, and that selectivity is called the regioselectivity. The region is selected if you did talk about that, right? Now, also you can say tertiary carbocation has more priority than the primary. Now we have this hanging around Cl minus will be acting as a nucleophile. So this nucleophile can go and hit the carbocation, neutralize it, and give you a neutral product. So simply I would say this is just put the HCl across the double bond, right? So like I mentioned, it could be going H goes to H. So H goes to actually more H. So it's kind of, we also call the rich gets richer. H goes to H, and it's also called the Markovnikov's rule, right? My students like to call it Mark's rule. It's so easier. Markovnikov is the one actually figured this out long before, but across the double bond like here, H goes to H, Cl goes to the other side, where the more carbocation, right? So H goes to H is a good way to remember, and or you should call it Markovnikov's rule. So this Makonikov's rule came actually hundreds of years ago, before we know about the carbocation. Today, we know about the carbocation. This primary is less stable than the tertiary carbocation, and the tertiary is the best. So today, using the potential energy, Gibbs free energy, we can actually show that, right? But further, more than that, we also want to look at how to apply more. EX, electrophilic, could be HBr, HI, HOH, HOR, HCN, and so on. You cut in the middle and stick across the double bond. Make sure you follow the Mark's rule, H goes to H, right? So you can practice like 6 different things for that one. So that's what we want to see. Now, the next part, we can also mention the explanation using the energy, right? Path A versus path B. So path A is very less, so it should be high activation energy. So it could be your y-axis could be potential energy, Gibbs free energy, enthalpy. Yeah, they all go in the same direction. So if I draw the path for A, it should look like that, primary carbocation, and let's put the reactants a little bit lower and the products in the other end, which is the chlorinated alkane, right? And then in pink, I'm putting the tertiary carbocation. It has more stability, like I said. If it is more stability for the tertiary carbocation, it has less energy and less activation energy as well. So we can look at that, and also we can finalize major product is the tertiary carbocation pathway. So that's how you want to look at simply how the HCl addition. The next one, actually, I will be discussing more stereo specific things if you need. Thank you.